we're back at 2.5. This is the first part of our lesson, and we're going to talk about graphing rational functions. One over my face. And man, I really missed this. We took this out of our Algebra 2 curriculum for the regular level track. Honors, you probably saw a little bit of this, but man, it's like one of my favorite things to teach. So, hey. We're going to be graphing rational functions. We're going to hear vocabulary like vertical asymptote, horizontal asymptote. We're going to find out when a rational function has a hole. Man, good stuff coming our way. So, first of all, a rational function is basically a quotient function. So there's a polynomial divided by another polynomial. And you don't want your bottom polynomial to be 0 because that would give you an undefined function to start with. So that wouldn't help. The domain of your rational function are all x values except for those that are excluded because of any discontinuities. So the bottom polynomial cannot be something where it'd be set equal to 0. Now we'll talk later about like what a hole means for a rational function, but asymptotes are the very large discontinuities. You're going to see vertical asymptotes and also horizontal asymptotes, and we'll talk about how we're going to find them. Now your textbook uses limit notation for asymptotes, which are just end behavior. So we'll talk about them so you can kind of interpret your book, but we're going to be using our regular end behavior, f of x approaches, blah, 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 notation. We're going to have to do a little bit of long division coming up where we have to figure out what are called oblique asymptotes. So, oi, it's going to get good. So lots of vocab coming up. Let's talk about how we find everything. So I think we are finally on your notes here. So here in your notes packet, we got some things to fill out. So polynomial function over a polynomial function, they can't have any common factors. If they do have a common factor, that means we're going to talk later about what that does mean. The numerator, okay, so the numerator polynomial compared to the denominator polynomial, you're going to compare the degrees, whether we're going to call them top heavy or bottom heavy or equal weight. That's going to determine what kind of horizontal asymptotes we have. But the vertical asymptotes are one of the first things you're going to find when determining what a rational function looks like. So in order to find the location of the vertical asymptotes, once you've factored all of the pieces of the numerator and denominator's polynomial and made sure there weren't any removable discontinuities, which are called holes, then we're going to figure out what happens when you set your denominator equal to 0 and solve. So any sort of solution that would produce a divide by 0, that creates an infinite discontinuity, those asymptotes that we don't like to see. And then horizontal asymptotes, we're going to have a little cheat sheet for this, by the way, but if you have what we call a bottom-heavy rational function where the polynomial that's in the denominator is larger than the polynomial that's in the numerator, so like maybe a quadratic over a cubic, or like a linear over a quadratic. In that case, your horizontal asymptote is going to be approaching y equals 0. If you have an equal weight where like it's the same kind of polynomial, quadratic over quadratic, linear over linear, in that case you have what we call full weight one, and it's just going to be the coefficient ratio. We'll see examples in a second. And then if you have a top-heavy one, okay, that means you have no horizontal asymptote, but there will be what we call an oblique. Oops, that's a Q. Oblique asymptote, which is a slant asymptote. Speaking of oblique asymptotes, it is the quotient answer when you do long division. So when you have a top-heavy fraction, it makes sense that we go through and do a division question. We're going to do long division, so sorry. And whatever the result is, you don't even have to find the remainder. I don't care about the remainder. I just want to know the quotient part of that. That is the equation for your oblique asymptote, which is slant. The X-Intercepts occur when you set your numerator equal to 0. Again, we've already taken care of any removable discontinuities or holes. And then the Y-intercept is where you just plug in a 0 for all your x's, and then you figure out what you got left for y. So let's see all of these ideas in action. Here's another little sheet about top heavy, bottom heavy. These are some nice examples of, this is bottom heavy. See how there's a bigger one in the bottom? It's quadratic. This is equal weight, quadratic over quadratic. So if you look at the coefficients, 2 over 1 is going to be our horizontal asymptote, so y equals 2. And then here, see how it's top heavy? We have a quadratic over a linear. That means we're going to have an oblique one. To be determined. Okay, reference sheet coming your way. Look forward to that one. I would like to jump in, for the sake of time, I'm real tired. I would like to jump straight into the examples that are on your notes. So, first one on your notes is something coming up. Keep looking. All right. So this one's kind of already done for you, but here's your polynomial function or your rational function. It's a linear over a linear, so we'll go back to that thought. But neither one of these factor, so there's no what we call removable discontinuities where they have holes. The vertical asymptote's what happens when you take your denominator and you set it equal to 0. So I used to tell my kids to set up an anti-equation. X plus 3 cannot equal 0, which means x cannot equal negative 3. Because there's a vertical asymptote at negative 3. So you notice on the graph over here, we have like a little dashed line here at negative 3, indicating the vertical asymptote. The horizontal asymptote is what happens when you compare the degree of the numerator to the denominator. Basically what you're doing is you're plugging in like gigantic numbers for x, and you're looking at what the limit is approaching. Well, if I plug in like 3 billion in for x, this negative 1 and plus 3 become negligible to the problem. So you're going to end up with like 2 times 3 billion over 1 times 3 billion, and the billion part will cancel, and you just end up with y equals 2. And then the x-intercepts would be what happens, oh, every time, would be what happens when you take your numerator and you set it equal to 0 and you solve it. So you notice they already did that here for you. So the x-intercept is going to be at 1/2, which I can kind of see. It's not done very well, but it's over there. And then the y-intercept is what happens when you go back to your original function and you plug in 0 for all your x terms. So basically I'm going to scribble out anybody who has an x, and look what I'm left with, negative 1/3. So you probably can't tell real easily here because it's counting by 2's, but the y-intercept is at negative 1/3. So again, back in the day of no calculators, or at least no graphing calculators, these were pretty tough. And you had to find as much as you could. And then you had to plug in some points by hand, because even then sometimes the functions were so weird that you weren't sure what they looked like. So you had to kind of be your own graphic calculator, and it was rough. This next example is, it's on your notes, so let's do it. So some wonderful person already came through and factored it for me, but I noticed none of these factors cancel. So good news, bad news, I don't know, but that's what it is. It says determine any asymptotes. So vertical asymptote, horizontal asymptote. We're not talking about obliques quite yet. We'll get there. They want to know x-intercepts, y-intercepts, and then they want to talk about domain. It doesn't even ask you for a range. I could. Let's talk about vertical asymptotes. That's what happens when you take your denominator and you set it equal to 0 or not equal to 0. So there are two numbers that would be a problem for my vertical asymptotes. The first one would be when x equals 0, and the next one would be x minus 6 equals 0, so x equals 6. So like, I won't be able to graph this. Too late. I'm too tired. I can't graph on a good day. Watch out, they are counting by 2's. Ooh, okay. Horizontal asymptote. I'm supposed to compare the degree of my original function. So this is a linear, and then this guy down here would be a quadratic. So if you think about plugging in something gigantic for x, like I'd have something gigantic divided by something even more gigantic because it's squared. So basically, when you take a number and divide by something huge, it approaches 0. So that's why you're getting a horizontal asymptote for a bottom-heavy one at y equals 0. That'd be this dude here. Highlighters work well for this step, by the way. X-intercepts would be when you set, every time, Abruzzo, when you take your numerator and you set it equal to 0, and you solve for that, and that gives us negative 2 for the x-intercept. So like, voila, right there. And then y-intercept would be, this one's kind of tricky because it's already factored, but if you plug in a 0 for the x's, you get 2 over 0 times negative 6. Well, don't think real hard about this, guys. You're going to get like an undefined number here, which means there is no y-intercept. And I'm going to go ahead and graph it. So through the magic of television or internet, I already graphed it. And it's going to look like, oh God, so ugly. Oh, terrible. Now, this other branch on the left side always kind of gets kids, because what happens is sometimes they think horizontal asymptotes are like magical invisible fences. That's not what they are. This guy does have an X-intercept. He comes through, but then he kind of comes back up and floats along the bottom side of the X-axis. So, like, don't panic if it crosses the asymptote. That doesn't mean like you did anything wrong. It's just one of these weird ones. So that is what it looks like. Lovely. The domain. Instead of doing interval notation for this domain, which we could, all right, I'll do it one time and then I don't want to do it ever again. The interval notation for domain is from negative infinity, and then we're good until we get to 0, and then there's a problem. And then we jump over 0, and then we're good until we get to 6. And then we jump over 6, and then we're good until the end of time. Well, I'm okay if you just write for domain x cannot be 0 or 6. So semicolon, it looks like a J. Sorry about that. So x cannot be 0, x cannot be 6. So that's, you guys are really good at interval notation. I have no problem with you just shortcutting it. Just be aware on a standardized test or in the back of the book or maybe in my key, I might have written it out in interval notation. No, we're going to skip it. But this is fascinating stuff. So you could go ahead and pause the video and read through this if you'd like. Oh, more. Pause the video and read through it if you'd like. I'm sure you're dying, right? Okay. This is my favorite list. So it's like, find the domain, sketch the asymptotes, blah, blah, blah. Okay, like they all kind of happen all at the same time until I get to the graphing part. And then once I get to the graphing part, I will sketch in things that I find. But after that, like, I'm just really dependent on my calculator because even I don't know what they look like sometimes, guys. So I don't have time in my life to waste getting points when I have a perfectly great graphing calculator who can get points for me or at least show me a picture of it. This is, I believe, on the back of your notes now. And we're going to be looking at a few examples where all I want from you is to find the domain, and then I want you to tell me if there's any vertical or horizontal asymptotes. So I do this in kind of a backwards order. I find the vertical and horizontal asymptotes first, and then I talk to you about domain. So we'll learn later that holes also create domain issues, but for us, the domain is directly related to the vertical asymptote. Speaking of vertical asymptotes, if I tried to set this equal to 0, I'd be getting like I solutions, and we're not going to worry about anything with I solutions in this chapter or in this section. So we're going to say that there is none. And then the horizontal asymptote is when you compare, the degree of the numerator to the degree of the denominator. So we have a constant over a quadratic. Well, the quadratic's much larger. So if I think about it being bottom heavy, remember our little cheat sheet for this? A bottom heavy ratio would indicate that the horizontal asymptote is at y equals 0. So because there is no vertical asymptote, when I say what is your domain, this particular case is kind of interesting. The domain is for all reals. There are no restrictions. Fun. All right, this next one. Again, I'm going to find vertical asymptote first. And then domain is going to be directly related to my vertical asymptote. So the vertical asymptote, if I took this denominator and set it equal to 0, I would have a vertical asymptote at x equals -1. Which, you know what, we'll go ahead and say x cannot be -1 for the domain. Remember how we're shortcutting it instead of interval notation. The horizontal asymptote is the comparison of the two functions. I have a equal weight function here. It's a linear over a linear, which means now I just look at the coefficient. So it's going to be at y equals 2 over 1, which is y equals 2. If they asked me to graph it, I sure could, but they didn't, so move on. And then here, vertical asymptote would be, the solutions to these guys. So x equals -1 and x equals 2, which for my domain, that means x cannot be -1 and x cannot be 2. And then for my horizontal asymptote, this is a quadratic down here. This is definitely bottom heavy. So my horizontal asymptote is going to be flattened out at y equals 0. Bottom heavy. not on your notes. So if you'd like to pause the video and kind of read through this, you go right ahead. This is straight out of your book, though. This says 2 vertical asymptotes means you have 3 parts. That kind of makes sense. It's almost like a piecewise in a sense where like you have these boundary restrictions kind of, and your function is going to have stuff happening on like every side of them. So just watch out. Sometimes our window on our graphing calculator isn't appropriate, so we have to kind of be careful. Okay, an oblique asymptote and a horizontal asymptote are both ways of us to describe end behavior. So your book does it with limits. We're not going to use limits when we answer them. I mean, if you want to get fancy and do one, then you go right ahead. Let's see. This one's not in your notes, however. I'm trying to see if there's anything very exciting about it. No. They're just claiming that if your polynomial in either your numerator or your denominator is not factored, they said you're going to need to go ahead and factor that. So, cool. Because you want to make sure there's no holes. But now they're going to ask you to determine all asymptotes, including any oblique. So did you notice at the beginning of this problem, I had a cubic divided by a quadratic? So this one is top heavy, which means that we're going to have to go through long division, which your book already did for you here. But they went ahead and they did long division. Well, I guess they didn't do a great job of showing it, so I'll show it over here. But when you, this looks really gross, but it's going to go kind of fast. If you do long division on 2x to the third, 2x to the third divided by x squared is 2x. Then we multiply, and you get 2x to the third, yucky, yucky, plus 2x squared minus 24x. What I like about these long division problems is you almost don't even have to finish them. So 0 minus 2x squared is negative 2x squared. It's become a plus 24x. So we repeat the process of division where I do negative 2x squared divided by x squared, and that's a negative 2. And actually, this is where you can stop, because my next step would be finding a remainder. And what you just found here is, that's the quotient. That is the line that is the oblique asymptote. So notice how they wrote their answer here, and they wrote it in that weird notation where they found the remainder and kept dividing it. This part right here is the oblique asymptote. So when we go to graph this on our graph paper, typically oblique asymptotes are just lines. You know, in this case, a slope of positive 2. Sometimes they're quadratic, not too often. Be careful. We're going to graph this guy. They didn't ask us to graph this one, but you would see after you got some points off your calculator that nice line of negative 2x minus 2 follows one part of the end behavior on possibly both sides. It depends on what's going on. Okay, hole. There can be a hole. Its official name is a removable discontinuity. It's removable because algebraically, once you have all the factors sitting there, they cancel out. Now, it's not like in normal algebra where things cancel out and then we just forget about them completely. Because they removed algebraically, they're still impacting the function as a whole, like literally as a whole, but the rest of the remaining parts of the function is what the rest of the graph looks like. So it's possible that you could have what you thought was a rational function, and it is, but because there's a hole for one of the factors, it ends up looking like a line, but it's got a hole in it. So, bit of bad news. Your graphing calculator does not show you the hole. It will show you that there's a discontinuity when you try to evaluate at that value, but it's not going to have like this big bright, like, oh, by the way, there's nothing here, because it's so minuscule that your pixels aren't going to pick up on it. So you have to be a savvy little algebra student or PreCalc student. So these examples here, I think this is the one that's on your notes here. So what they did is they took that original quadratic up in the corner and they factored it. And then do you see how the x plus 2's cancel? So they went ahead and showed the cancellation. What that tells me is that this causes a hole. And where it says x cannot equal negative 2, that's the solution to that factor. That's because there is a hole at x equals negative 2. So what you're going to have to do is figure out like where's exactly the location of the hole. So I know negative 2 is the x value. What you're going to do now is you're going to go back to the rest of the polynomial You're going to plug in a -2 in for all the x's. So they did that down here. -2 minus 2 over -2 minus 4, and then it turns out it's at 2/3. So when it's really quite annoying. So you're going to go to the graph paper, and then at -2 2/3, you're going to draw like a really exaggerated open circle. And if you're like me, it's not even going to come close to actually being in the right spot. But if it's relatively in the right spot, that's good enough. The whole point of it is, can you determine what is removable, and then what does that do to the rest of the function? Because like at first glance, a lot of kids tell me there's a vertical asymptote at -2, and that's not right. There's a hole at -2 instead of a vertical asymptote, so we got to be careful. Let's see some examples here. I think that particular question they went through and they actually finished it. Oh, this one looks like a hoot. Let's try this one. So I know there's lots of factoring that needs to happen here, so let's quickly factor. This is x minus 7 times x plus 3. And then this one factors really nicely by... No, it doesn't. Oh my gosh, guys. So irritating. So in order to factor this one, I had to cheat. I'm going to be honest, I cheated big time, and I graphed it. I typed just this polynomial into my y equals, and I saw all the places where it crossed the x-axis. So bad. And then I kind of reverted back and wrote them as factors. So remember our hard work with the rational root theorem? Yeah, I was too lazy to like confirm them in any algebraic sense, so I just cheated. Sorry, my old PreCalc teachers would be so mad at me. Alright, so this is, turns out there's a solution at -3, so x plus 3 is one of the factors, and x plus 1 is another factor, and then x minus 2 is the other factor. I'm sure there's lots of cool ways to factor that, but I just... Alright, so forget that function piece, forget this function piece. Let's look at the components here. Anybody here remove? Oh, yes, right here. X plus 3s are removable discontinuities, which means that we have a hole at x equals -3. That's the solution to that factor. But in order to determine the rest of the hole's location, you're going to take -3 and plug it back into the remaining function, which is x minus 7 over x plus 1 times x minus 2. So plugging in a -3 everywhere, you got -3 minus 7 over, oh gosh, -3 minus 1 times -3 minus 2. -10 over, see, that's -4, -5, what is that, 20? Well, that's not too bad. That's -1/2. So, watch how fun this is. At -3, -1/2, you're going to draw like a very exaggerated open circle. The holes are not that big. You wouldn't be able to see them. It's just because I'm old and I'm grading your paper, you're going to make like a really big one. And then after here, we're going to be able to answer all the rest of the questions. So, determine any asymptotes. So let's see if we have vertical asymptotes. Sure do. Now don't worry about the removable discontinuity part, but I do have two vertical asymptotes, one at x equals -1 and another at x equals 2. And then as far as like the horizontal asymptote, when you're comparing the denominator and the numerator, some people like to go right back to the original function. Some people go to this like new reduced version. It doesn't matter, because either way you canceled a term for another term. So you still have a bottom heavy fraction. So you're still going to have a horizontal asymptote at y equals 0. So whoopie. And then they want to know intercepts. So let's start with my x-intercept. Remember, the removable discontinuity is not incorporated anymore. So if you take your new numerator instead of equal to 0, you get an x-intercept at 7. And then your y-intercept is what happens when you plug in a 0 for your x value. I would just go ahead and say, like, it doesn't matter, again, whether you go to the reduced version or not. So it's... do this to you, but it's actually easier if you just go way up to the original and just cross off like everything that has x's, like gone, and then you just look at the constant part that's left. So -21 over -6 is positive, gosh, 7/2. That doesn't feel right. Yeah, it is 7/2, which is 3.5. So what I should have been doing this whole time is actually plotting these things I'm finding. So x equals 7 is an x-intercept, y-intercept of 3.5, asymptote at x equals -1. Oh gosh. X equals 2. Oh no, so bad. If I had one wish, it would be to be better at drawing. Horizontal asymptote at 0. I forgot something. All right. So, I would cheat at this point, use my calculator a little bit. Turns out, this dude, now don't go through that hole there. That's one branch. And then there's like a weird little parabola looking thing here. I don't know exactly how far it goes down, but it slides along the asymptotes there. And then this one's kind of weird. So like this is one of those cases where like it comes up through the x-axis and then comes back down and flattens out. So I don't know if that thrilled you at all, but that's what that function looks like. The important part is to find all those components. So I'm going to ask you on a summative to like explicitly find the whole, vertical asymptotes, know the difference between them. I will ask you for domain and all that good stuff. This one's fun. I do see it's top heavy, so we're going to have some long division over here. I'm going to go ahead and take care of that now if you don't mind. Oh well, I probably didn't have to do this, but that's okay. So x squared plus, where are we at? X, oh yeah, I do. I thought it factored for a minute. It does, but nothing cancels. At first glance, I kind of thought there was a hole in this problem. There is not. All right, so we're doing some long division. X squared divided by x is x. And then x times x plus 1 is x squared plus x. Don't forget you're subtracting. Well, that's lovely. Nothing. That guy right there is the body to the oblique asymptote. So if I just throw a y equals in front of it, that tells me that my oblique asymptote, hey, that's pretty good, is right there at y equals x. Happens to be the identity function that was, by design. It's not anything special. I quickly in my head factored this, x plus 3, x minus 2, and then I saw x plus 1, and I saw that there were no removable discontinuities. That's why I went ahead and did the long division. If you did the factoring and something canceled, in this case, it would have ended up with like just looking like a line, but it would have had a hole, so be careful. You still have a hole with it. Anyways, I digress. I think there is one on your book that looks like that. They want to know about vertical asymptotes. I can see that there's going to be one at x equals -1. So this dude, sorry. We don't have any horizontal asymptotes because it's top heavy, but we totally had an oblique asymptote at y equals x. And then there's no holes. X-intercepts would be if you set your numerator equal to 0, so -3 and 2 were my two x-intercepts, so -1, 2, 3, and 1, 2. Y-intercepts would be what happens if you plug in a 0 for all these x terms. So kind of simplifying down to -6. 1, 2, 3, 4, 5. Oh man, it's off the graph. Okay, sorry about that. And then from here, I would kind of choose my calculator. So, spoiler alert. Oh gosh. Okay. See, this is why someone like me, really, oh my gosh, I'm gonna quit. Really needs to draw in the asymptote lines because you can't graph like. So bad. Look. I don't know if you can see this, but like, there you go. See that? Like, I did like a super good job of graphing it, like on paper and pencil. I'm awesome. On this, so bad. Okay, so this is not any surprise to my kids who are in my class. Like, they know how bad I graph. Anyways, I'm done. I'm done for the night, guys. It is like pitch black outside, and I'm tired, and I'm gonna go to bed. We are gonna work more on graphing. Don't be surprised when like every single example we do in the future, like as a whole, might have an oblique asymptote as well, has multiple other asymptotes. Just one thing to remember is that yes, your graphing calculator is super helpful in determining if you're on the right track, but it does have its limits. Like it won't easily show the holes. It won't easily identify the actual equations of the oblique asymptote, so you can kind of get a guess for it, but you do have to do the algebra to kind of confirm all this. So it's not like we're wasting our lives doing these by hand. I mean, we talked about the SAT ad nauseum, where there's a whole part of it that's no calculator. And I can confirm with you that your calculus teacher is going to want you to be able to do a whole lot of this by hand. So I have a point. I swear I have a point. All right, good luck.